The MELODI framework, a novel tool designed to monitor and analyze energy usage during the inference phase of large language models, LLMs, addresses the growing environmental and economic costs associated with LLM operation. By leveraging scafandry and NVIDIA SME, MELODI tracks CPU and GPU power consumption for LLM processes, facilitating a deeper analysis of the relationship between task complexity and energy utilization. A robust dataset was created to evaluate MELODI's capabilities, featuring diverse prompts to monitor energy consumption of various LLMs across different types of instructions. This dataset includes energy consumption measurements, metadata such as prompt and response sizes, complexity, and time metrics for each inference process. It aids in exploring the relationships between prompt complexity and energy expenditure. The research contributes to the development of a framework integrating open-source tools for monitoring power and energy consumption, an extensive data collection initiative involving multiple LLM deployment frameworks, and a generalized analysis elucidating the relationships between prompt characteristics and energy consumption patterns observed within the collected data. The background of LLMs is also discussed, highlighting their significance in natural language processing and deep learning. These models, trained on vast text datasets, learn intricate language patterns and relationships through unsupervised learning, predicting subsequent text from context. Advanced APIs and deployment frameworks facilitate the integration of LLMs into digital ecosystems, allowing developers to utilize LLM features for prompt submission and response generation. The paper emphasizes the importance of advanced monitoring tools and technologies for tracking and optimizing energy consumption, thereby mitigating the environmental impact of AI operations. MELODI employs scafandry and NVIDIA SME for their complementary features, providing detailed insights into the energy usage of computing systems at the process level and real-time monitoring of GPU, including power consumption, for systems equipped with NVIDIA GPUs. The MELODI framework systematically samples prompts from a curated collection, submits these prompts to an LLM, and records prompts, responses, metadata, and energy metrics during inference. The dataset used in this study includes alpaca and code feedback datasets, featuring a diverse range of prompts tailored to enhance instruction following capabilities and refine code execution. The dataset obtained using MELODI is analyzed to address three research questions: how the energy consumption of LLM inference varies across different hardware, models, and prompt datasets, how the energy consumption of LLMs changes as a function of the number of tokens in the input prompt, and whether the energy consumption of LLMs can be predicted using the input prompt's characteristics. Here is a combined summary of the content from pages 58. The study investigates the energy consumption of large language models, LLMs, during inference processes, examining the impact of model size, hardware configurations, and prompt datasets. The analysis reveals that larger models, such as Llama 70B and Llama 370B, exhibit significantly higher energy consumption per token compared to smaller models, with a substantial difference of roughly 100 times more energy per token. Hardware configurations also play a crucial role, with laptops showing higher energy demands than workstations, primarily due to CPU processing inefficiencies. Moreover, the choice of prompt dataset influences energy consumption, with the code feedback dataset leading to higher energy use per token compared to the alpaca dataset. To explore the relationship between prompt complexity, response characteristics, and energy consumption, the study derives 57 text-based features using Python frameworks and integrates them with the energy consumption dataset. The Pearson correlation coefficient is calculated, revealing that response characteristics, such as token length and duration, are strongly correlated with energy consumption, whereas prompt complexity features exhibit low correlations. The study develops machine learning models, specifically random forest models, to predict energy consumption based on prompt or response characteristics. The models using response token length demonstrate high predictive performance, with R2 scores greater than 0.97, while models relying on prompt characteristics exhibit limited performance. The findings emphasize the importance of optimizing response generation to reduce energy consumption and highlight limitations, including the accuracy of power usage monitoring tools and dataset size constraints. Future research directions include utilizing precise power measurement tools, exploring LLMs for energy consumption prediction, and investigating the connection between prompt complexity and energy consumption. The analysis on pages 9 and 10 discusses the energy consumption of large language models during inference, emphasizing the need for energy-efficient practices and the importance of understanding the relationship between response quality and energy consumption. The authors propose a comprehensive framework, MELODI, for real-time energy tracking and optimization, leveraging tools like Scafandry and NVIDIA. This framework is demonstrated through data collection on various LLM architectures, hardware setups, and prompt datasets, contributing to the optimization and sustainability of LLM applications. The authors acknowledge funding support from the European Commission and reference studies on sustainable AI and energy-efficient computing. The discussion on pages 11 and 12 begins with the energy costs of large language model inference, referencing Siddharth Samsi et al.'s work. It then transitions to environmental risks and benefits of large language models, referencing Matthias C. Rillig et al.'s work. The section also covers energy and policy considerations for deep learning in NLP, as presented by Emma Struble et al., and the taxonomy of risks posed by language models, as detailed in Laura Weidinger et al.'s work. The summary concludes by mentioning part-time power measurements and the OpenCode interpreter, showcasing the diverse range of topics covered in the research.